Hey guys, today we're going to tackle exponential equations. And I think what's really cool today is these exponential equations are extremely practical and relevant to solving a lot of everyday type of practical problems. And the number one tool that we need to solve these questions is actually some of our logarithmic properties. So we've kind of been building up to this moment, and this is going to answer one of those questions anyway, of why in the world do we have to study logarithms anyway? And today's one of those reasons. So what are we going to see in this video? We're going to look at, here's two examples, and on the surface they may look fairly similar. On this first example, we've got a base of 2 and a base of 16, and we're going to talk about a method that where we rewrite both sides using the same base and then equate those exponents. Okay, now that method doesn't always work, and that's what we're going to see in the second example is we've got a base of e, and then we're going to end up with some other crazy number over here once we isolate that term, and we won't be able to express both sides with the same base, and we're going to talk about using our natural logarithms there in that example. So anyway, what exactly is an exponential equation? How do I recognize one? How do I know that I'm dealing and trying to solve an exponential equation? And basically, this is just any old equation that contains a variable in the exponent. So if you see your variable in the exponent, and again, you're going to have a constant number as your base. So like you've got a base of 5 and then your variable's up here, or you got a base of 3 and then your variable's up here. Here we've got a base of e, which is a constant, just like the 3 and the 5 were, and then you got your variable up here in the exponent. So those are all your cues and your indicators that you're working with an exponential equation. In this video, kind of we hinted at, we're going to look at two techniques to solving exponential equations. One where we can express both sides with the same base. Unfortunately, that method isn't always going to work. When it does work, it's great, but it won't always work. And then we'll go to method number 2, which is where we use our natural logarithms. So if we focus on the first method, we're using the same base. And again, it says sum. All right, some exponential equations can be solved this way by expressing each side as a power of the same base. So we've got b raised to the m equals b raised to the n, and the only way that this side could equal this side is if those exponents are equal to each other. So now if we had a base here and then a different base over here, we wouldn't be able to set those exponents equal to each other. So that's our goal. We're just going to try to, rewrite both sides in this form. Usually we're going to have to manipulate one side, but sometimes we're going to have to manipulate both sides. Once we get there, we're really in good shape. We just set those exponents equal to each other. We solve for x or whatever the variable is, and we're off to the races. So let's see what this looks like. The first example, and I think when you're trying to think of like, what's my common base going to be on both sides? It's usually a small number. It's usually like a 2 or a 3 or a 4. You always want to work your way down. So when you see a big number like 16, you're thinking, okay, I'm going to work my way down. How can I express that using a base of 2? And if you'd agree with me, we know that 2 to the 4th power is equivalent to 16. So I'm going to use that, and I'm going to replace the 16 with a 2 to the 4th. So we've got 2 to the 3x minus 8 equals 2 to the 4th. We've got the same base on both sides, so I'm going to set this exponent equal to this exponent. So we got 3x minus 8 equals 4. 3x equals 12. I told you we're off to the races once we get there. The hardest part by a mile is just, replacing that 16 with 2 to the 4th and recognizing that. So we get x equals 4. Real easy check. We could substitute that 4 back in for x. Real easy check to confirm that we do have winner, winner, chicken dinner. Okay, next example. Here's an example where we're going to probably have to manipulate both sides and rewrite both bases, because I'm thinking they both can be rewritten with a base of 3. So in my back pocket, I know that 3, whoopsie, let's go. Okay, we know that 3 squared equals 9, okay, and we know that 3 cubed equals 27, so this bears tailor-made. Let's replace this 27 with 3 cubed, and then rewrite that original exponent. And then we're going to replace that 9 with 3 squared. And now here's the biggest key. We just got to remember to distribute, because I'm multiplying these exponents, right? So I got to distribute that 3 to make 3x plus 9. I'm going to multiply here, distribute, so we get 2x minus 2. And then we're just going to solve. I'm going to subtract 2x from both sides. And then I'm going to subtract a 9 from both sides simultaneously. So I get an x over here, I get negative 11 over here. And you're wondering, is negative numbers okay? Are they okay? And in this case, well, there's certainly on the surface, there's nothing wrong with a negative. You just want to plug it back in and check it. And again, it's a real easy check. Plug that negative 11 right here, and you'll be able to confirm that it does check. So now we're going to kind of graduate to method number 2, and most exponential equations cannot be rewritten so that each side has the same base. That's unfortunately the reality of that. And logarithms are extremely useful in solving these equations. This is kind of like our safety net. And in fact, I could have used these natural logarithms on the previous 2 examples. You could just say, you know what? I'm just going to get really good at this one method. I'm not even going to worry about that first method you just taught us. That's okay. So here's our little checklist, our little cheat sheet. We're going to isolate the exponential expression. That is a skill in itself that may be a little harder than it sounds like it's going to be. And we'll see that in our last example. But you want to isolate that exponential expression. Once you do that, we're going to take the natural log of both sides. Now, technically, does it have to be the natural log? No. It technically could be any log that you want to use. I want to encourage you to get in the habit of let's just say from this point forward, we're going to use natural log whenever we can. And then here's where the magic comes into play. We're going to use that power property that we learned for logarithms recently. And it says, okay, if you've got the natural log of b to the x, you can rewrite that exponent where it's moved out as the coefficient. So it's x times the natural log of b. We're going to take advantage of that property. And then from there, just solve for the variable, right? Solve for the variable. So here's the situation. I can't rewrite both sides using the same base because, 3 to the whatever equals 13. I don't know. So I'm going to go ahead. The step number 1, the exponential expression, is this expression right here. So he's already isolated. Now, what you want to watch out for is, if there was another number here like 5 times 3 to the x, you would have to divide that 5 over first and then take the natural log. But we're ready here. We can go ahead and take the natural log of both sides. So we've got natural log of 3 to the x equals the natural log of 13. Rewrite the exponent out front. And then divide both sides by the natural log of 3. Holy smokes, how easy is this? And if we're going to probably just go 3 decimals on all these answers, my calculator is saying 2.335. And again, really easy check here. Just substitute that back into x. Now, in this case, because this was not an exact answer, when you type in 3 to the 2.335 power, it won't equal 13 exactly, but it'll be ridiculously close and close enough to give you a lot of confidence that we do have the right answer. Okay, so here's an example where isolating that exponential expression is a little tricky. I think we'd all look at this and say, okay, we definitely have to add the 5 over, right? But do I have to do something with the 40 first? And the answer is yes. You have to do something with the 40 before you take the natural log of both sides. And here's why. You have to ask yourself, who exactly is being raised to the 0.7x power? And in this case, there is an implied set of parentheses right here. Only the e is being raised to the 0.7x power. So what I have in pink parentheses right there is considered your exponential expression, right? So that's who we have to isolate. So we're going to add that 5 over first and foremost. So we get 40e to the 0.7x equals 280. Then we'll divide by 40, okay? We're dividing both sides by 40. That's going to give you e to the 0.7x equals 7. Okay, now we've isolated that exponential expression. We can go ahead and we're going to take the natural log of both sides. So we go natural log of e to the 0.7x equals the natural log of 7. All right, move the exponent out front. So 0.7x times the natural log of e. If you ever have a brain fart, you could type this into your calculator, but hopefully remember that ln of e is just a 1. So we have 0.7x equals the natural log of 7. And then just divide both sides by 0.7. So x equals the natural log of 7 divided by 0.7. Notice we're not dividing by the natural log of 0.7. It's just 0.7. And when you type that in your calculator, this is actually a little challenging rounding question here. I first got 2.77987, and I'm trying to round to 3 decimal places. So I'm looking at this bear, which rounds this bear up, which is going to have a little domino effect. And we're going to go 2.780 when we round it properly. Okay. All right. Hope you feel pretty good about these two methods. Time to go put it to use and practice these suckers.